This is HAQAST, Massachusetts, Session 3A, Emerging Ground Networks for Satellite Data Integration, with moderator Ted Russell kicking off the session, talking about the Atmospheric Science and Chemistry Measurement Network.
So if you look there, ascent, that's, you can read it as quickly as I can talk. And this is, we've got these 12 networks out there, and it's actually growing. That it started, and we're now getting real live data coming in from all these networks. And what it's meant to be is a long-term network where we're really developing some very advanced information about aerosols. So with that in mind, the 12 stations are across the United States, even up in Alaska. Jingchu is in the audience. It's up there in way up north, and I'm sort of from about as far away from that as you can get in Atlanta. But you see all these sites across the United States with different, sometimes co-located with NCORE sites, sometimes, well, actually there it says what they're co-located with. So it's these, what we've done is we put out this advanced instrumentation at all these different locations that are teamed with other pollution networks. So you can sort of see what there are. You can see who the different investigators who are leading at each of these sites and sort of why we chose them. And so you can see that they have a bunch of different sort of attributes that essentially can leverage the information we're getting from it. If you look at what we've got out, we put out these 4 different types of instruments: TOF, aerosol chemical speciation monitor, which will give us the non-refractories. Primarily, it'll give us compositional information on the organics as well as some of the inorganics. An exact, where we're getting sort of the elements. Sometimes they call them metals, but it actually goes beyond the metals. An ethylometer for black carbon and wavelength dependent absorption, so we can get black and sort of brown carbon. And then an SMPS where we're getting size distribution. So it's a lot of extra information that is going to be coming up out of that. And this picture is now, I think, 2 weeks old is about it, because this is the first information coming from all of the different sites. And so you can really get an appreciation for what sort of information it'll give you in the future. And we have some value added products going in, and I'll really point your attention to the second one, where we're going to be doing online source apportionment, sort of near real-time source apportionment. I suspect one of the questions is going to be one other thing is, if you look at the application of this network to the Maya mission, you can see that we overlap it in a number of cases. So with that, one thing I was going to say is the data is going to be posted for essentially the community to start using, and hopefully it's going to start rolling in after that. So it's a really exciting, at least to me, network of these 12 sites, and the data is going to be coming available very soon. So that's what's happening on this one. And what I want to do then is call up Jeff Geddes to talk us through some other exciting network opportunities that are coming.
Thank you. Cool. So I'm one of the 36% for whom this is their first HAQAST meeting. And I wasn't sure necessarily exactly what to show. So I figured I would just kind of keep it high level and talk about the Pandora measurements that we've heard about a few times already today. So some nice introductions there. And maybe just go over some kind of examples, simple examples of where these Pandora measurements can really help support interpreting tempo measurements and other satellite observations. So here you see 2 of them out in the wild, one in the roof of my building in Boston and one on the roof of the University of Utah in Salt Lake City. So the Pandoras are ground-based spectrometer systems that kind of look like this in cartoon form. And they collect spectra and then analyze the spectra to look for these absorption features of the same trace gases that we retrieve from satellite measurements. So they're a nice kind of like measurement to have on the ground to support satellite observations. And they can be operated in a few different ways. One of the most mature retrievals and simplest ways to operate these instruments are in direct sun mode. So in this mode, the instrument follows the sun and looks at the direct solar beam and retrieves the trace gas from that direct beam. Because we're not worried about contributions from scattered radiation, this retrieval is fairly simple, and very well constrained because we don't need any special assumptions to go into the retrieval. You can also operate these instruments in a sort of diffuse sky mode, which just means you're not pointing at the sun, but you're pointing anywhere in the sky and collecting the scattered radiation. So not looking at the direct solar beam, but scattered radiation from the sky. And because that means you can point in any direction at any angle, it's possible to retrieve vertically sort of resolved information because you can point at different zenith angles. And that goes all the way down to a sort of near surface product. You can imagine kind of pointing almost horizontally at the sky towards the horizon and retrieving the column density within that near surface column to get a near surface concentration. However, this version of the instrument requires some more assumptions because we have to factor in the fact that we're only looking at scattered radiation. So you have to think a little bit about radiative transfer and so on. So the exciting thing is that there are many of these instruments out in the wild now, probably on the order of 100 sites. The exact kind of coverage temporally at any one site, you'd have to kind of investigate for yourself, but this is kind of a map of what things are looking like. So my instruments at BU, we have 4 instruments, two of which are in Boston, 2 of which are in Salt Lake City. But these instruments are operated by PIs all over the world, and we kind of together form a global network called the Pandonia Global Network. And you can go to this website, check out the data, and learn more. So what could we use these observations for? The first kind of obvious thing I guess I thought I would point out is, simply for satellite data evaluation. The simplicity, especially of the direct sun retrieval, means it's a really nice reference measurement because it's not relying on any of the assumptions that are required to go into the satellite-based retrieval. So it's sort of like a real kind of measurement to compare against the satellite observations. And so I'm sure you'll see lots of papers that do this kind of stuff. We've done this at Boston University where we compared tropomi overpasses on top of my building with the Pandora measured column nitrogen dioxide. And what's interesting, what you can learn about even a simple comparison like that is under which conditions do we expect the satellite measurement to be representative of what's happening at the ground on the same spatial scale. And what we found in Boston, for example, is that depending on the meteorological condition, you can tell whether the satellite pixel average is actually representing what you might measure at an exact location on the ground. But under other meteorological conditions, there's heterogeneity that's happening that inside that satellite pixel. That means that what the Pandora is measuring at one particular location may not be that representative of what's within the satellite pixel average. And that was especially true under sea breeze days in Boston, where we have very complex kind of mesoscale meteorology operating on spatial scales that are smaller than the satellite pixel. And so it introduces a lot of, you might say, oh, on sea breeze days, the satellite is performing poorly. But actually what might be happening is that there's just so much more mixing happening in a horizontal space. But on days with systematic westerly conditions, there doesn't seem to be any kind of bias or problem because those days are much better mixed. These instruments are also great. We've already seen this today for examining local scale variability in the ratio between what's at the surface and what's in the total column. And another thing that we kind of discovered at Boston University about this relationship is that because of the different forcings that drive variability in these different parts of the atmosphere, they can really, the measurements can really diverge. So at the surface, what we found in Boston in a lot of days, especially when they have a sea breeze day, just at the exact same time where the boundary layer is growing, and so your surface concentrations are getting diluted with sort of free air from above the boundary layer, your surface concentrations will decline. And that temporally happens to happen at the exact same time where the sea breeze brings pollution from the city over our site. And so the column measurement can increase as the surface concentrations are decreasing, which is what you'd expect from that measurement. And so making these ground-based measurements help you understand that relationship at a local scale and over time. You can also kind of deploy multiple of these to also examine the spatial relationship between surface and column measurements. And so in Salt Lake City, we've collected some really beautiful data. We have a site at the University of Utah, which you saw, and one sort of in the southwest part of the Salt Lake City basin. And we can make these measurements and say, okay, well, now that we're making a ground-based measurement of the total column in the atmosphere of nitrogen dioxide, how does that relate to the actual spatial gradient of nitrogen dioxide at the surface where we actually are breathing the air? Even if we're not able to make an exact quantitative relationship between the concentrations at the surface and the column, can we at least say that the average spatial, sort of like the relative spatial gradient, those two are the same? And so when you look at the surface concentrations at the university compared to the surface concentrations at the site in South Jordan, you see that the university site is always more polluted. How much more polluted on a relative scale depends on the time of day, but because it's closer to downtown, that site is always more polluted. This is under a specific atmospheric condition, actually. But when you look at the column measurements that we're making with the Pandora, you see that actually the spatial gradient we're measuring in the column might not even match on a relative scale the spatial gradient that's happening at the surface. And that depends on the time of day, the meteorological condition. And even when we look at Tropomi overpass time, what we found is that while the university site is on average more polluted than the other site at the surface, 50% of the time in the total column, the gradient is in the opposite direction. So even making a sort of to a simple approximation, an argument that the spatial gradients might be relatively similar might not always be the case. And the Pandora measurements help you kind of measure that, understand it, and figure out like when it might be the case and when it might be less the case. We've also deployed these instruments in a capacity where multiple instruments might be within the same satellite pixel, so we can directly measure the spatial variability of nitrogen dioxide within an individual pixel. What I'm showing you here is a long-term average from Tropomi with boxes that show you day-to-day changes in the Tropomi pixel. So about half the time, our Harvard instrument was in the same pixel as our BU instrument. And of course, many of us might already expect lots of variability spatially in nitrogen dioxide in the surface concentrations. It's something that's well measured, well understood. But there's kind of like, we're not as sure how much of that spatial variability actually finds itself in the total column. And this gives us a way of measuring it. And so when we compare the measurements, depending on when you look at Tropomi overpass time or other times of day, the comparison of these two instruments within the same pixel might be similar or might be very different. And again, that often relates on very local conditions. And so looking at Pandora measurement on average across a large region might not actually be true in any individual local case because every case will depend on meteorology and kind of local conditions. I mentioned that you can operate these in this sky scan mode. So we can actually retrieve vertical profile information for something like nitrogen dioxide. Here are some examples from Salt Lake City. And in this case, we can retrieve these profiles multiple times a day. So almost on an hourly basis, we're learning about the vertical structure of these pollutants that might help us interpret the satellite measurements. You can see on the far right, we had this instance of very rapidly varying kind of abundance of nitrogen dioxide at altitude. We get this little pocket of high NO2 that only lasts for a few hours. And the shape of this profile might be important for understanding the satellite measurements accurately. And we can retrieve multiple things from the Pandora. So here are just some time of day plots for formaldehyde, nitrogen dioxide, and their ratio on summertime weekdays and summertime weekends, just to demonstrate that we now have also a ground-based constraint on things like formaldehyde to NO2 ratios and maybe monitoring the spatial variability in those ratios, how they might be representative of ozone pollution chemistry, and so on. So I'll just end with some thoughts on, I wasn't sure how familiar people in this room might be with Pandora data. It sounds like very, which is awesome. But I will just sort of warn people that if you're not used to these files, they can be kind of hard to wrangle. And so I would encourage partnership with people who are operating these instruments. Every instrument in the PGN has a local investigator who's in charge of that instrument. They've paid for that instrument. They have students who are working on making sure the data is quality. So you should partner with them to understand the measurements the best possible. And they'll just end with some of the usage guidelines for the data. With that, I'd be pleased. I could talk about Pandoras for a long time, so I'll stop there and you can email me or find me later, or we can talk about it after. Thanks.
Thanks, Jeff. And I forgot to mention Pawan Gupta, one of the HAQAST members, is unable to be here. So we're going to move on to Sarah Kroening from the Children's Health Alliance of Wisconsin.
Thank you. All right. Okay. Okay, so thank you all. I am Sarah. I'm here from Children's Health Alliance of Wisconsin. We are affiliated with Children's Wisconsin, which is a hospital system in Wisconsin. And we are focused on being a voice for children's health and being really proactive in trying to come up with ways to help children and families across our state. And I'm specifically here on behalf of the Environmental Health Initiative. So we're looking at factors that are in their environment and ways that we can be proactive in focusing on helping them address those factors. So today's focus for our session is our newest program called Love My Air Wisconsin. I've actually presented about our program in the past at the last HAQAST conference, and I'm honored to be here again today. I'm going to take some time to share some updates on how we plan to incorporate satellite data into our air quality education programming. So I wanted to first start off, in case you haven't heard of our program yet, with a high-level overview of what we're doing. So we are replicating a program that started in Denver. Actually, other states are now starting to look at incorporating this program in their state as well. We are just finishing up our first year of implementing this program. We focused on Milwaukee to start because we are aware that Milwaukee has the highest asthma burden across our state. So being with the Alliance and looking at asthma data, we wanted to make sure that we were providing a program that could be starting in a place where it's needed the most. So we're currently partnered with Milwaukee Public School District, and we are focused on teaching students about air quality and its impact on health. And in order to do this, we are installing air sensors on schools free of charge. And then we are also providing a dashboard and app, which I'm going to get into in a moment, lesson plans, tools such as personal air beams that they can also use, and then the satellite layer that we are creating with our dashboard to enhance student learning. And we're also attending many events, as many as we can, at schools across the city to also engage with the community, not only to share this information directly with families, but then also gain feedback as we are developing and continuing to create this program and adapt it for Milwaukee. So the Love My Air dashboard is one of our exciting new tools that actually was started by Love My Air Denver. So we are just adding onto their network of sensors. And again, we are focusing on sensors that either are at schools or are closely aligned with schools. So it makes it a unique dashboard for students to be using and community members as kind of a bridge to air quality because it provides information in a very simplified manner. And so as you can see on this would be like a homepage that the students can come into where they see their logo. So they select the school that they attend, and then it can take them either to this map view or even a different image where it's just the air quality of that day and then the recommendation that goes with that air quality. So with this, with our dashboard, Brad Pierce from UW-Madison in the Space Science and Engineering Center is offering to help add a satellite layer to this dashboard that can be used by students as a tool. And so I then connected with Brad and his team to talk about what this dashboard is and how we can work together. Through some of those conversations, which we just had recently, because this app and dashboard, our Love My Air Wisconsin is just joining this. So this is all very much in the works as we speak. But we met recently to go over what does this look like for the Love My Air dashboard. And they were very patient with me as I asked many questions because this is not my area of expertise. And through this conversation, realized that not only should we be looking at the AOD layer, but adding more of a visual for students to understand and really grasp what's going on, because when there, as you guys have been talking about throughout these sessions, when there are clouds and we can't see the aerosols on the satellite information, for myself, somebody that's not as experienced in this area, and especially for our students, when we think about this could be used for first graders through 12th grade, that visual is going to be essential into helping them understand what's going on. And so we're looking at adding multiple layers on this dashboard. We talked about a movement feature, but we're at this point not sure that it's going to be available just based on the capabilities of the dashboard. So when we look at about incorporating this information into lessons and helping students to really have an access and understand how to use this tool, I wanted to give some background on what I currently have available and also just kind of the basics of developing lessons. So I don't know if you all are familiar with Bloom's taxonomy, but it is a foundation to creating lessons where teachers look at that critical thinking skills level, and it's broken down into categories. And so that basic foundational level is just really like kind of rote memorization, where they're remembering, recalling facts, defining, repeating, listing items, and it advances to the higher critical thinking skills where they're able to apply their knowledge in terms of like creating the next step. So they're producing original work, designing, assembling, those types of things. And so the current lessons that we have, I partnered with Subject to Climate. They're an organization that has a panel of people, including scientists, that review the lesson plans. So you can be sure that the lesson plans anybody's accessing are of high quality. And they follow a model that you incorporate into the lesson, which is inquire, investigate, inspire. So along the way, you are automatically including this kind of higher level critical thinking skills to really understand the information that you are learning. And so right now, just again, we're in our first year. So I created a lesson for K through second grade and then third through fifth. So the students are looking at understanding the basics of air, looking at how to access this dashboard and what it means for them. And then also applying that to the impacts it has on their health. And then as the grades progress, this information becomes more and more analytical, exploratory. And so especially at the high school level, the national standards include information that look at health systems, that look at space and sciences across the United States. So currently for one of our the lesson that's in the third through fifth grade, students are provided a link. I think I might have skipped a slide. I'm not sure. Okay, sorry. So here, for the air quality and your health, the third through fifth grade, there's station work that's involved. And so one of the stations is actually related to geography standards. But students will then go to the purple air link that's provided in the station, and they look at exploring real-time air quality. And their goals are to compare different places and analyze images of those cities to infer why the air quality is the same or different. They can zoom out and look at air quality around the world or search images of different cities, and then infer why air quality is the same or different in those places. And then they synthesize why is air pollution different depending on where you live and people's actions in response to air pollution in that area. So that leads to incorporating the satellite data layer, where then they can use this as an extension to that work to compare these images and provide that higher level thinking as they synthesize why is air pollution different depending on where someone lives and how might they want to respond. So thinking about especially the wildfires that have been occurring, this will give a visual of like where is air different and how is it moving as they look at what's happening each day. And so this was just one image I grabbed from the purple air that they would be looking at, and then what eventually will be on our dashboard. And then they can reflect on questions. As you see similarities, what do you think might be causing the air quality to be different? Is it from a local source or is it coming from a natural event? And then again, when you think about the high school aspect of all this, kind of jumping ahead on them, on high schoolers exploring this information, they would be able to use this layer, incorporate the data. And so they'd have hands-on real-time opportunities to interpret real world data. And it makes it more engaging, but also helps them develop important analytical skills, especially as it relates to health and environmental justice concerns, and helps them gain a deeper understanding of the factors that affect air quality in their area. So some next steps is to create short trainings that help teachers understand how to use this tool that will be on our dashboard. Provide lessons that explain how to incorporate this tool, because I can say from personal experience, when this is not your area of expertise, it is pretty intimidating at first. So really making this accessible for teachers to learn quickly and then apply into their classroom. We have some amazing partners, not only within the state of Wisconsin, but in other areas too that are going to be using this dashboard, who are really excited about this data layer and how we can incorporate it into information and with their work. And then gaining feedback from teachers and students to make sure that what we're providing is relevant to what they need in terms of exploring this information and then adjusting as needed. So information that's a link to our website, but then also my information as well. So look forward to learning from the rest of you guys. Thank you.
Thank you. Thank you, Sarah. Our next speaker is Randall Martin, who's also a HAQAST PI from Washington University.
Thank you, Ted. So, let's see. Right. Oh, you do see it full screen. Okay, perfect. So I'd like to talk about the surface particulate matter network today. And this is motivated by something I suspect you all well understand, the immense health concerns associated with long-term exposure to PM 2.5, with millions of attributable deaths each year that are valued at trillions of dollars. And recent lowering of the WHO guideline or EPA standard provide renewed awareness and of the significance of this issue. But despite the importance of PM 2.5, vast areas around the world have grossly inadequate ground-based monitoring for exposure assessment, which leads to satellite remote sensing as an important information source to fill those gaps. But the relationship between aerosol optical depth observed from satellite and ground level PM 2.5 is complex. And as a result, the Committee on Earth Observation Satellites, known as CEOS, has recommended co-locating ground-based measurements of both aerosol optical depth and PM 2.5. But despite hundreds of ground-based sun photometers measurements of aerosol optical depth, or thousands of PM 2.5 monitors, in the absence of Spartan, only a handful are co-located. And that has motivated then the creation of the Surface Particulate Matter Network. It builds upon that well-respected sun photometer network of AeroNet that accurately measures aerosol optical depth from the ground. And in densely populated areas of relevance for health, adds a PM 2.5 monitor. That monitor has been designed to be highly autonomous to reduce the burden on the remote operators, featuring a removable cartridge that is preloaded within our central laboratory at WashU, shipped off to each remote site, where the operator could insert it into the instrument, let it run, unintended for a period of time. The instrument cycles through the different filter slots, avoiding a traveling blank. Upon completion of sampling, the operator can return that cartridge to our lab for analysis of the chemical composition on those filters. The default instrumentation package also includes a nephelometer that offers high temporal resolution, and more importantly, offers information to decompose the relationship of AOD with PM 2.5. Thanks to a number of partners worldwide, we've been fortunate to sample at about 30 sites to date. Again, site locations prioritize densely populated areas of relevance for health. There have been about 10 new sites added over the last couple years, largely in support of the Maya satellite mission to be forthcoming, in which Spartan is one of the validation networks for that mission. And although this network was designed for that purpose of measuring the AOD to PM 2.5 relationship, because that relationship needs information on the chemical composition of PM 2.5, the Spartan has become the only global network of the chemical composition of PM 2.5, thus offering valuable information about sources and health effects of PM 2.5. There have been a number of major advances over the last few years, including upgrades to the analytical instrumentation involving a robotic weighing facility in an environmentally controlled chamber. We've switched from ICP-MS to X-ray fluorescence for better characterization of mineral dust. There have been upgrades to the ion chromatography instruments. Organics are now measured by FTIR. We heard about this from Ted Russell introducing it for the Ascent network. This is by Ann Dillner at UC Davis, a key leader in the IMPROVE team. There are also in progress streams for using aerosol mass spectrometry and UV-Vis spectra. A key theme of this network is to maximize the information that we can obtain about the chemical composition of PM 2.5 from each one of those filters brought back from each different site. So it involves that gravimetric assessment for mass before sampling and after sampling. Then there are a series of non-destructive optical measures, many at WashU, some at UC Davis as part of the IMPROVE team, in order to connect the same measurements made by IMPROVE with those by this network. Those key ones are HIPS, a measurement of black carbon, and FTIR that we spoke about. There's also an elemental characterization through X-ray fluorescence you heard me speak about. Then there's a subsequent destructive step in which the filters are sonicated into a water extract. That's primarily to feed the ion chromatography instrument for assessment of anions and cations. There's also two research streams, one for oxidative potential and one for nebulizing that extract into an aerosol mass spectrometer to obtain additional information about organics. I'm showing you here an overview of the recent PM2.5 chemical composition data that's been collected as part of this network. The numbers inset are showing the PM2.5 mass concentrations. They're varying by over an order of magnitude, so there's a very large signal to assess here. And then surrounding that is the chemical composition that's obtained from this network. There's a lot to talk about here. I don't have much time. I'll focus the next two slides on two aspects of this. First, trace element oxides. It's fairly perceptible on this slide. And second, on black carbon that seems surprisingly large to us. First, turning to the trace element oxides. So these are the measurements from X-ray fluorescence that characterize the elemental composition of PM2.5. That can be used to infer mineral dust in yellow, and that's through a global mineral dust equation. But I want to draw your attention to the trace element oxides in light blue. Those are normally small, normally less than a microgram per cubic meter, but can be large. For example, in Dhaka, 6 micrograms per cubic meter of trace element oxides, which is really quite large. On the right, you're seeing the result when we incorporate those elements into the EPA health risk assessment model and the associated cancer risk. So with arsenic being a driver, cadmium, cobalt are also important, as well as lead. The black line is the adult 1 out of 100,000 cancer risk, and red line is the result for children. So there are concerning levels of hazardous elements for cancer risk. The next one I want to talk about is black carbon. The horizontal axis is showing the measurement of black carbon from HIPS. This is also done concurrently by IMPROVE. The vertical axis is showing the simulated black carbon using a chemical transport model called GeosChem in what's called its high performance configuration known as GCHP. This is enabling a global simulation at 25 kilometer resolution is what you're seeing here. And what you should see in blue is showing the results for developed countries. So the United States, Canada, Israel, South Korea, Australia, and overall a very tight R² of 0.8. I find surprisingly tight. There is a bias in the slope of a factor of 2. We have yet to well understand that. But then the red is showing the results for developing countries. And here you should see a substantial degradation in skill. These are primarily across the global south. We've been concerned about whether representativeness bias could play a role. In other words, could black carbon be sufficiently heterogeneous within each model grid box that it would lead to some bias? So we've conducted a simulation at globally 12 kilometer resolution, so C720. This is very computationally expensive, so we did it for 2 months, January and July. We find the same conclusions. We've also wondered whether this is an anomaly in SEDS, so we've tried substituting in HTAP or EDGAR. Again, we get the same results. So we believe there's a lot to learn about black carbon across the global south in order to represent its concentrations for both air quality and for climate. Also remind you of those concerning levels of trace elements that we're finding at different sites. and of the rich emerging data set from Spartan, offering information about the chemical composition of PM 2.5 that's of its own value, and also for further understanding the relationship of aerosol optical depth with PM 2.5. Thank you.
Thank you, Randall. And the last speaker for this session is Dan Westervelt from Columbia University.
All right, so I'm going to talk a little bit now about well-calibrated low-cost sensors or air sensors and what potential they have for enhancing the utility of satellite retrievals for air quality management. So first of all, just a little bit of background on air sensors. One of the big challenges of using air sensors, of course, is do we trust the data? Is the data any good? And so a lot of what we've been working on is figuring out ways that we can build trust in these air sensors and improve the data quality, especially in places where a lot of data doesn't already exist. So places in the global south. I have some pictures here of some places across the African continent where we've been using air sensors tested against reference FEM methods and validating them and developing correction factors and things like that. And so that can be really valuable for closing the air pollution data gap around the world, especially in the global south, alluding to what Randall had just talked about a little bit. We've done this in other places as well. And I think, it's not just the global south. There's many locations in the global north where we still lack a good bit of surface air quality data. And so there's a lot of potential. We've been, working a lot on evaluating the performance of a lot of the different air sensors that are out there just on the consumer market. And so this is some results from a co-location project that we did in Ghana. And so they're basically there's 4 scatter plots up there, but 3 of them are the sensor on the y-axis versus a reference method FEM on the x-axis, basically just showing, the agreement between the 2 data sets for PM 2.5. All right, so if you have the best agreement, then these, there should be good alignment here with these lines here, which are the 1-to-1 lines. You can see my pointer right now. And you can see, it depends on which type of sensor you're using, but there's definitely some variation there, and there's definitely some error and bias in those data. So it's important to recognize that as we embrace the whole low-cost sensor movement. It's important to know what is the accuracy, and can I apply any corrections to it. So I showed that for Ghana, but we've also been doing this a lot in the US. And this is an example from New York City at the Queens College site, which was mentioned earlier here. So our group was actually the first to bring low-cost sensors to the New York State Department of Environmental Conservation at this site. Since then, there's been tons and tons of groups that are kind of doing similar things. But what we did is we just co-located some purple airs against their NCORE site, which has all the instrumentation you could ever ask for. And so we just sort of demonstrate that with this comparison with this co-located data, you can generate correction factors that can give you high quality, actionable information that moves towards FEM quality. So for example, the blue lines here on this plot are just the raw purple air data that you would get out of the box. Sort of the yellow is the FEM FRM, which I believe at Queens College is a TEOM. Yeah, and then the red is the corrected purple air, and you can see the red, traces pretty well with the FEM FRM are, and so the statistics also kind of bear that out. So we're doing this all over. This is an example at Lamont where I'm based at, Columbia Lamont. We have the Air Sensors Lab, where we're doing a bunch of co-location studies with some just off-the-shelf consumer sensor brands, but also kind of building our own. So this bottom right here is a picture of kind of a homemade air sensor for PM and a couple of gases as well. And so for the PM, we can compare that to a reference monitor. And in this case, we use the GRIM EDM 180. So what role, back to sort of the title of my slides here, how does this tie into satellite data? And so Of course, we all know, I probably don't have to tell this room that the big issue is that, satellite gives you some columnar information. And what we really want is the breathing level information. And it's been mentioned several times here for sort of the Randall Martin approach, which works very nicely, where you can take GeosChem output and do an AOD to surface PM 2.5 conversion. Another approach, of course, that I think actually was mentioned in this room a little bit earlier today was developing statistical models that can create sort of an empirical relationship between surface PM 2.5 and column AOD. And so both of these things have been tried out, and with the latter, the machine learning is becoming a big player in this arena as well. But I think that sensors in particular, air sensors, can, if they're well calibrated, can be useful sort of ground truthing or training data to build these conversion factors. And so that's exactly what we've been trying to do, and we've been focusing this on places where normally you don't really see this kind of study happening. So a lot of times the training data for this conversion from AOD to PM 2.5 is based with the wealth of data that we have in the US or in Europe or in other data rich areas. Other parts of the world, not so much, but because of the efforts of various groups around the world, there is now, in my opinion, enough data out there to begin to try these type of methods in places like Africa. So this is an example of what we did in West Africa in particular. And we basically just take the AOD and then PM ground-based data from some sensors, but also for some reference monitors from US embassies and consulates around the world, which is a great resource for air quality data in data sparse areas. And then we can train an XGBoost model to predict out surface PM 2.5 based on these satellite input parameters. And looking at the results, it's actually quite promising. So this is some plots here, time series plots showing the observed ground-based PM 2.5 in orange versus the ground-based observed is in blue, and in orange is the model predicted with XGBoost. And just by scanning quickly over the figures, you can see that we're sort of capturing all the main spikes and seasonality and things like that. The statistics kind of bear out a similar story. We have a high R squared if you kind of add all this up, and relatively low error and bias. You can also, one thing that I think is really cool about this method is, and again, this is nothing really new, it's just maybe not really has been applied much over Africa or other data sparse areas, but you can go back through the historical period. So as long as there's satellite data, you can go back and say, okay, I can run my XGBoost model and get sort of a longer term trend in what the PM 2.5 looks like. And so this is for, this plot is for Burkina Faso, for a major city there, where we were developing this XGBoost model, and we were able to get PM 2.5 data. In this case, this is, I think, annual mean PM 2.5 data on the left, and then monthly on the right, since about the year 2000. So you can also get high resolution output that looks like this, basically, and this this has a lot of applications, I think, for epidemiological research, for policy implications, environmental justice. And so we're doing some of that in West Africa, and particularly in Ghana, with some collaborators from the public health field. So yeah, I'll just summarize. The growing hybrid observational networks of surface PM 2.5 over Africa and other traditionally data sparse areas can be used to do this AOD to PM 2.5 conversion. And a lot of times, a lot of this data is used with, can be used with relatively low cost or medium cost, maybe well-calibrated air sensors. So I recommend that this sort of methodology is applied and maybe benchmarked more in the global south as more of these data sets are coming online. And we've been able to get some pretty promising preliminary results for West Africa that suggest that this may be suitable for the kinds of analysis that have been going on in HAQAST over the US for years and years. So with that, I'll stop and take questions. Thanks.
Thank you, Dan, and don't leave. And I'd like to thank all of the speakers and now invite them down to be part of the panel and open it up to questions both online as well as in the room. And is someone watching the computer to? Great.
I have a question to start, if that's okay. So I'm always kind of curious about explaining this data to the public, and when it's like you have this satellite data and you have this low-cost sensor data, and you have these other data sources, and thinking about like the educational aspect of it is, you know, how do you frame, you know, how certain these different data sources are, and like when to trust them or not, or how to best use that data for a more general public understanding?
No. I can take a stab. Yeah. Well,
Who's that for?
So, I mean, it depends who you're speaking to, but I would try to imply that it depends also upon the objective that you're trying to achieve. I think general rules of thumb are that something that is on the ground with an instrument designed to measure that specific quantity is likely to be more accurate. I would then imply that something that is more remote sensing based likely has more assumptions. First from the ground and then from satellite has more assumptions. And a model is the one that is really probably most uncertain, but is the one that has predictive capability and the what if scenarios where one can explore alternative scenarios. What if we reduce traffic by a certain fraction? What might be the expected result? Or what if the climate would change, or as the climate changes, what might be our change in air quality? So I would just, if I was answering that question, I would try to do so in a way that helps the user think about the different data sets, where they're coming from. I don't know if there's a right answer from my point of view, but that's how I would think it through. Others can probably do better than I just did.
Yeah, I agree with what Randall said mostly. I'll maybe just chime in from the sensor perspective, since that's most of what I talked about. Yeah, I think there's a real conundrum with air sensor data, because a lot of regulatory agencies will not be too happy when like their citizens report they have a purple air in their backyard and the levels are 500, and they're like, what's going on here, you know? And the reality is that like the user is putting it right above a barbecue where they're having, you know, their Memorial Day barbecue or something. So there's a lot of variability in like the sensor stuff that you have to really look out for. But more generally speaking, I think that, you know, that just using the uncorrected raw ground-based sensor data is probably only best for like qualitative things, you know, just is the air quality in like the yellow AQI or the green AQI or the red AQI. You really need to provide some, you know, sort of correction factors if you want to be able to do quantitative analysis with it.
And I'll add to what Randall and Dan have said, is that I think this is where it calls for dialogue with the people who are doing those measurements and the people who are running those models as to what they're really good for. And, you know, models come in tons of different flavors. Some are much more accurate than others in terms of, and a different approach, be they empirical or deterministic, whatever, you know, chemical transport models or receptor models. And also, you know, when I look at some of these networks, they're actually research instrument grade instruments that are, you know, that people are going to be spending half a year evaluating, verifying that data that gets posted. Whereas some others are going to be the more low-cost sensor, where it is much more you're taking the multitudes versus the accuracy of a single instrument. So it's a dialogue thing to me.
Hello, good afternoon. Jesse Marquez with the Coalition for Safe Environment. We're an environmental justice organization, 23 years old now. In the next 30 days, we're going to have a low-cost network of 5 monitors up and running. In my community, Wilmington's approximately 4 miles square. So it just so happens we're honored with the largest polluting port in the United States, Port of LA, as our neighbor, and then the second largest polluting port, the Port of Long Beach, and then we have 4 oil refineries in Wilmington. On the subject of calibration. Now, so you know, we do have a PM sensor in it. That's better than Purple Air, better than Clarity, so we're a little bit grade up on that. So we will be doing 1, 2.5, and 10. We want to do a little bit of greenhouse gases, a little bit of VOC. So on the greenhouse gas, we went with an ozone, carbon dioxide, and methane. On the VOCs, we went with benzene, toluene, and formaldehyde. But my question is on calibration, okay? Every manufacturer is going to send it to you. We test it at our lab. It's certified. And then I'll say the best quality type monitor say, but you should also calibrate it at your site. And then do an annual calibration or as frequency as you might determine during that network. That's the little fuzzy area we're not that great on understanding. Because if we're going to calibrate it on our site, what's different? You know, the instrument is supposed to be calibrated to do what it's supposed to do at manufacturing. And now you're telling me to calibrate it on my site. You know, what's going to be that big difference? And then if I do want to be able to correlate it with some of the Temple satellite data, then what other type of calibration should I be looking into or consider?
I guess I can start. Okay, so
It's Centroid, Ottawa, Ontario, Canada.
oh, cool. Yeah. So I think those were all some really good points. You know, the question of like how local should your calibration be is a bit philosophical sometimes, more than like, you know, exactly guided by the, you know, the scientific details. And so what I mean by that is like, you know, if you're having a co-location site and then you're testing, you're evaluating, you're getting your statistics, and then like where you want to deploy it is in the same city, but you know, 5 miles away or something. A lot of times people just go with that. They're like, that's good enough. We don't need to, you know, they're willing to assume that like the environmental conditions are consistent enough between this area of the city that we don't need to like have a separate co-location like in such a reasonable proximity to where the first one was. I think that it's
Square.
Yeah.
So refinery.
Yeah.
And then our office north, and then just south in the middle will be the ports. But
Yeah.
all with-
I mean, I guess it's very application specific as well. I mean, just to highlight something you did say about like the manufacturer calibrations. Yeah, I think those, I personally choose usually to like do also my own calibrations just because I'd rather have some control over like the length and the parameters and you know, things like that. So I think that's something to be careful about as well, is maybe not always just kind of blindly trusting what the manufacturers do for their correction factors. There's a lot of great resources in Southern California with the HAQAST program, which I'm sure you're pretty familiar with. But yeah, I mean, we can talk more offline if you want, but yeah.
I have a question for Ted and the Ascent Network. I attended the Aegis Plus workshop and there was some discussion about smoke and ozone production. And, you know, it seems like the Ascent Network paired with some of the CO, regulatory CO and ozone monitors could play a big role in at least scientific understanding of that. And I was just wondering if the network or any PIs have plans for that.
And you'll see that coming out in the first publication. I'll just put it that, well, not the first one. The first one's already out. But yes, we are, and one of the things that was neat is that we were actually able to capture some of the smoke episodes, again, coming through from Canada, hitting North Carolina, et cetera. And so we see that very clearly in our data. So, and is it turns out the Atlanta and Great Smoky sites were very much put there to look at some of the smoke episodes in the southeast, and then you have the Los Angeles-based triad that are also looking at fires in that area as well. So yes, we're looking. That was one of the main objectives of the sampling strategy. So we are looking at that, and you're going to start seeing that come out.
I have a question for Jeff. I thought the NO2 profiling from the Pandoras you showed was pretty interesting. How often do you do that? And has there been thoughts of, with the PGN network, of operators doing that on a consistent basis or a consistent timing or things like that?
The frequency of those profile measurements are kind of up to each individual investigator. But I will say that sort of if an investigator isn't thinking too much about it, there's sort of a plug and play schedule that the instrument will come on with the people who do the retrievals. So in my case, I didn't think too much about it beforehand. So those retrievals are collected roughly every hour. It's a little bit less than every hour. And so the timing is somewhat inconvenient, but an investigator could schedule it exactly however they want. And in fact, they could also point the azimuth, sort of the horizontal direction you're looking at, in any direction for those profiles as well. So the short answer is there's a default schedule that if you're part of this PGN network, your instrument will sort of be on, but the individual investigator might also decide that they want to put their instrument on a different schedule for research purposes. And one of the things I wanted to try to highlight is that because every investigator might have their own research priorities, that also means that this global network that you see a map of sort of, it's not misleading, but it's just sort of like, it's not the simple story, because every instrument might be doing slightly different kind of things with a different schedule, and might have been offline for 6 months and because the instrument was moved. And so every site that you look at, you kind of have to really evaluate, like, okay, in what direction was it pointing to collect the vertical profiles? And if there's multiple profiles, were they looking in different directions so that I shouldn't even really be comparing them or assuming they're the same? So it kind of depends on the location, the individual investigator. For tempo, there's discussions right now for that default schedule to sort of, whether there's ways of making that default schedule kind of work with the tempo overpasses. So like maybe you're collecting a profile shortly before or after the tempo saw the site. You don't want to sacrifice the direct sun too much, because also the direct sun measurement is sort of the most accurate measurement. And so actually the direct sun might be what you want to time exactly with tempo, because then you have this like ground-based sort of reference that doesn't require assumptions of the total column that you can then evaluate tempo with. And then maybe 5 minutes later or 10 minutes later, you do a quick kind of vertical profile measurement to think about that. But think for NO2, things can vary so rapidly in such little time that even a 5-minute offset can occasionally change, your interpretation of the satellite measurement. Does that answer your question?
Yeah, thanks for complicating my head a little bit.
Yeah.
I appreciate that. Yeah.
Yeah. It's just an interesting patchwork network that everyone is sort of in charge of it. It's unlike other networks that are, put together where there's a very kind of set priority in terms of the operations of that instrument so that you can always compare them. So yeah, but there might be movement towards that.
We have a question from Sadie N from the Zoom. They say, thank you all. This is very exciting. Many of these programs are focused on areas of high population density in order to serve as many people as possible. Those outside of metro areas have noticed the lack of investment and opportunities to join programs, and it's eroding the already fragile trust in both science and government. What does the future of these programs and services look like? How might these programs differ from metro programs? When can rural communities expect to be engaged with?
I'll just say on the Ascent network is that we're somewhat equally divided between high population centers as well as more rural. So we're trying to get a balance there. And actually, I should have said in response to the former question, pretty much all of our sites are smoke impacted, just in particular some of the rural sites. So we are looking at that to get get an estimate of what's happening in the less populated regions as well.
In case this is for Love My Air, we're starting in Milwaukee with the hope that we can find funding to expand across our state as well, because we know there's an interest in air quality across our state, so.
Since we're passing along for Spartan, it's really cost driven. We're trying to find measurements that have the effect upon the largest populations. So that's why we're starting with densely populated areas. If there are more resources, we'd be quite happy to expand into more rural areas.
Yeah, so with my sensor work, we are looking a little bit into some rural areas, especially places where there might be manufacturing or energy generation. So we've done some sensor work in a rural community in Eastern Ohio, which has been it's been affected by fracking and oil and gas industries in general. So there's been some of it, but as Randall said, I think the first kind of attempt is usually kind of the urban population.
I'll just add, that's where models and satellites come in, because we are never going to have enough measurements, ground-based measurements out there. And so we need these other tools. These tools are there to enhance what we're getting from satellite observations. So I think that's the real key, is that there's other tools out there to make these measurements relevant across the board.
Yes, hello, Ben from the National Science Foundation. And this returns in part to the first question, but also is sliced through all. I read a paper recently called Why We Need Lower Performance Climate Models. And I'm wondering if you can make a case for why we need lower performing air quality observations instead of trying to fit where the low-cost sensors fit into the better data. Is there a space or knowledge that we're gaining with them that is just not available in other places? And can the case be made that we really need these lower performing observations to get at questions that we have otherwise unable to answer?
Yeah, I mean, I don't know that this is going to be the most satisfying answer to this question, but I would argue that we don't want lower performing at all. We want high performing and low cost. And so that's kind of what we've been trying to do, is can you extract useful, actionable data out of things that are, normally just off the shelf consumer products. So I think, the lower cost stuff really helps democratize air quality data. You don't really need a lot of money or a lot of expertise. But yeah, I think the framing, the way I frame it is like, we want high performing, but low cost.
I'm just going to quick add too, from the community perspective of, when we install these sensors across the city of Milwaukee and explain that this is like on a school, it's really bringing the awareness to the community versus like when there's this regulatory sensor that's not in their area. It's just helping to bring this awareness and engagement with this information. So we found it helpful in that form.
All right, thank you for the nice talks. I have a question for Dan. For your satellite machine learning model, have you tried more sophisticated algorithms such as deep learning? And also, do you think your model can be generalized to other regions, or do you have to train regionally specific models for each region?
Yeah, so the reason that we undertook this work was because we didn't really think that all of the currently available methodologies out there are necessarily, appropriate for specific regions. And so therefore I wouldn't really want to, extrapolate like this model tuned for West Africa. I really wouldn't want to extrapolate that elsewhere. I think that, the products that, or the stuff that's already out there from, Randall, for example, I think is already got that well covered. And then, yeah, the other question about, different machine learning methods. I mean, the short answer is no, we haven't tried many other, approaches. We found some good results with XGBoost, and I think we didn't want to sort of make it too much of a black box. We wanted to at least try to keep it somewhat grounded. And so, you know, we could definitely try additional machine learning models, but I think we're fairly happy with the results we're getting right now. Yeah.
Okay, so I have a question. So if I understand, mostly objective is to get data either from NASA satellite or from logo sensors or from modeling perspective. So my first question is then, like, nowadays there are a bunch of sensors and everyone is building sensors. So this is getting harder and harder, which type of sensor we should use, whom should we trust, right? So then now looking to the field and looking to people who are working in local sensors, what should be your sort of actually 2 points? Hey, look, this type of sensors are more reliable and are easily deployable. So this is one, my question. And then second is basically you are now, like, there are actually people who are in chemical transport model, other people who are doing the global scale model with satellite data, third category people are using local sensors. So is there any platform through HAQAST or someplace where you have team of modeler where you can communicate with each other so that maybe bring up solution using maybe modelers from maybe local sensors who are building traction equation, people from, you know, some ODs, PDs, chemical transport model, some people who are using satellite data. So is there any platform where, you know, they all should sort of actually collaborate to bring more data using all these sort of resources?
I feel like I've hijacked this HAQAST meeting for sensors, so sorry about that. Other questions are allowed. So yeah, I'll just start and then maybe pass it on. I think the question of like what sensors do we use and who do we trust and all that, it is very difficult. I will point to that there are a few like international consortiums out there that are seeking to answer and deal with these very difficult questions. And maybe that I would sort of point you to them. I actually run one of them, so you can just talk to me later. But there's also IGAC has the International Global Atmospheric Chemistry group has a new effort on air sensors, and they're tackling these exact questions of what's the difference between a purple air and a clarity and a quantIQ and a whatever, and yeah. So I think maybe I can point you to some of those, but yeah.
I wanted to kind of elaborate on the question, the Zoom question about rural sampling. So I know NASA's just recently selected one of the EVS missions, which is going to be looking at agricultural emissions, NOx emissions and things. So it does seem like as you're thinking about these kind of federated networks, think about what's already out there from an agricultural perspective. We've got all these agricultural research stations, got full met, got surface flux measurements and things like that. And think about adding trace gas and aerosol sensors to those. That's a network that's out there, already has a lot of the information you need. And I think it would help build out that agricultural component.
I'm going to have to follow up because I'm one of the 3 members of the leadership team of that EVS proposal. So I'm just remembering that one of my items of, one of my jobs was to connect with Luke and John Walker and talk about the ground observation network and maybe thinking about Pandora plans, but sounds like you might also have some good tips. So yeah, that's exactly true.
Okay, we have another question from the Zoom chat from Puneet Kolipara. They ask, how much might black swan pollution generating events like industrial fires or a wind-induced dust plume throw off the performance of the aforementioned ML models, in parentheses, high-res ground-based PM 2.5? How do you account for that possibility in training, tuning, and refining the models? Or do they already account for those potential discrepancies with little additional fine-tuning or feature engineering needed?
I think that's you again, Dan.
So I had trouble hearing all of it, but it sounded like the question is sort of about how do like certain extreme like dust events impact these measurements and also like various use cases of the sensors. Is that sort of along the lines?
Yeah, I think the question is really focused on how the machine learning models are affected by extreme events, like
Yeah.
industrial fires or wind-induced dust plumes?
Yeah. The way that we've designed the machine learning models is pretty much not anything really out of the ordinary from like their base implementation into whatever your favorite Python library is. So I don't have any pithy comments on like how we've handled extreme events and things like that. I would think that the machine learning models should be able to roll with that when there's high concentrations. They can deal with that. I mean, I know that there's some methods that have trouble extracting data beyond what the training data is, but I don't think that's a problem necessarily with the methods that we're using. I mean, dust in general is a problem for a lot of sensing applications. Most of the available consumer available sensors out there don't have any ability to see large particles like supermicron particles. So if you're sort of building that into a machine learning model, then the underlying physics are going to be flawed anyway. And so the machine learning model is not going to be the problem. It's more of like what the base training data is. Yeah, I don't know.
Yeah, and just to reiterate that point, many of the lower cost sensors, even not just the low cost sensors, have trouble with the coarse 2.5 to 10. So if you're interested in the dust problem in particular, that becomes a real problem with a machine learning approach or not. They do get saturated also in some real strong dust events.
Yeah, I'll share the ways we've been thinking about that in deep learning. So just to preface, when Dan introduced our algorithm, he described the first part of our algorithm. We follow that up with a deep learning step. And that deep learning step, we do a few things. One is we bring in geophysical information that would provide information on those physical relationships. Another one is to conduct a buffered leave one out cross-validation. So the point here is to avoid any spatial autocorrelation. So for example, if two monitors are located a kilometer apart, they will, for PM 2.5, they will have a tendency to exhibit very similar variability. And so what we'll do is we'll exclude from evaluation all of the monitors within a 100-kilometer radius or variable radius around the test site, and thus offer a better test of the performance of that machine learning algorithm. So subject it to a more stringent testing environment. Those are some of the ways we've been thinking about. I'm sure there's more that could be done.
Hi, this question is for Dan. I have a question about the low-cost sensors that you're building through your project. Now, I work for the Department of Health in Hawaii, and we have an NCORE station in Kapolei, right? And so with NCOREs, we measure various parameters, and I believe that you're developing a parameter that measures Vox. So how does that compare to like the NCORE, like the expensive equipment of like NCORE and the equipment that you're developing, as well as if there's any corrective factors that's comparable to what you've done with Purple Air and the stations that you've measured in Queens College?
Yeah, so the sensing technology for particles, I would say, is a lot further along in its sort of capability and reliability than gases. So you can certainly apply some of the same methods, like you can apply regression or machine learning to correct, like for example, electrochemical cell gas sensors when you compare them to, like a chemiluminescence NOx analyzer or something, which is probably the method that NCORE uses. And I don't know if that's true everywhere, but you can certainly do that same thing, and it kind of works pretty well. But there's a lot more problems, I would say, with the gas sensors in terms of like their selectivity. A lot of them are cross-sensitive to other things, especially if you're going to try to monitor like VOCs, for example. There's no selectivity at all. The chemical cell will react to basically anything that has 2 carbons and some hydrogen. So like all the VOCs. So yeah, it's a little bit more of in its infancy, but there still are some good studies out there and some good approaches to get useful data out of the gas sensors too.
And with that, I hate to cut off the discussion and the questions, but it is time. So I want to thank all of the speakers again, and I want to thank the audience. Thank you very much.